Okay, good afternoon. Let's have a look at the solutions to our last assignment. Okay, question 1, graph an inequality 4x minus y over 2 less than 6. All right, to graph this inequality, first of all, we need to find the boundary line, right? So we can use equivalent transformation. The original inequality is equivalent to 8x minus y less than 12. Usually I don't like ratios, so I just multiply the 2 to both sides, which gives us the new equivalent inequality here. Next, we can separate the x and y to get y is larger than 8x plus 12, right? Okay, so the corresponding line is y equals 8x plus 12, right? This is our boundary line. So next, we need to plot this line. Best way to plot it is to find its x and y intercepts. So when x is 0, y is 12. This is one of the 2 points. The other point is when y is 0, we know x is 3 over 2, right? Okay, so now we can draw this line on the 2D Cartesian plane. Okay, x-intercept is 0, 3 over 2. So 3 over 2 is here. Y-intercept is 0, 12. Okay, suppose 12 is here. Again, this is not necessary to scale. As long as you ensure each element has correct relative positions, you'll be fine. Sorry, it's not 12. Should be positive. Should be negative 12. Sorry, there's a typo. Here. Should be negative 12 here. So when x is 0, y is negative 12, right? So next, negative 12 is here. And because the inequality states that y is strictly greater than means at the boundary line, the region does not include the boundary line. So we need to use a dotted line instead of the solid line, right? So the line should like this. And the corresponding region is here, which is up to the boundary line. Okay, any questions? No? All right, let's see question 2. Again, first of all, we need to separate x and y in order to find the boundary line in the slope-intercept form. Okay, so the original inequality is equivalent to y plus 3 less than minus 1 over 2x plus 2, right? And which is further equivalent to y is less than minus 1/2 of x minus 1. And corresponding line is y equals minus 1/2 of x minus 1. So again, when x is 0, we know that y is minus 1. This is our y-intercept. And when y is 0, we can solve that x is actually -2. And this is our y-intercept, right? Okay, so now we can draw the line on the 2D Cartesian plane here. All right, y-intercept is 0, -1. So suppose -1 is here. And x-intercept is -2, 0. And suppose -2 is here. Okay, let's check the inequality. Inequality says y is less than or equal to. So this time we need to use the solid line instead of the dotted line, right? Because the boundary does include this line itself. Okay, and corresponding region is, because it says y is equal to or less than, so the region is under this line, right? Okay, any questions? All right, let's see question 3. What is the maximum of x plus y? And there's a conditions. X is greater than or equal to 0. Y is greater than or equal to 0. 2x plus y is less than or equal to 8. And x plus 2y is less than or equal to 10. Okay, so this is a typical question, typical linear optimization question, given these 4 conditions, which we need to maximize x plus y, right? Okay, so we start from each of the constraints. Let's label them with 1, 2, 3, and 4. And we need to find the corresponding region to these 4 inequalities, right? So let's start from the first one. The first one is simply x equal to or larger than 0. So the corresponding boundary line, let's call this line 1, is actually x equals 0, right? This is very simple. And for constraint number 2, again, similarly, the boundary line L2 is just y equals 0. It's also a simple case. Okay, case number 3, 2x plus y less than or equal to 8, right? Okay, again, we need to separate x and y. This is equivalent to y is less than or equal to -2x plus 8. And then the corresponding boundary line, let's call this L3, is y equals -2x plus 8. And in order to draw it on the 2D Cartesian plane, usually we'll need to find its x and y intercept. So when x is 0, we know y is 8. And when y is 0, we know that x is 4, right? Okay, so this gives us the necessary information to draw line 3. Okay, we'll leave it later. Let's see condition 4 first. For number 4, x plus 2y less than or equal to 0. This is equivalent to 2y less than or equal to -x plus 10, which is equivalent to y less than or equal to -half of x plus 5, right? Okay, so the corresponding line, let's call this L4, is y equals -1/2 of x plus 5. Again, in order to draw it on the Cartesian plane, we need to find its x and y intercept. When x is 0, we know y is 5. And when y is 0, we can solve that x is 5, x is 10, right? Okay, so let's draw these these 4 lines on the 2D Cartesian plane now, and then the corresponding region. Okay, first line, x is 0. This is just the y-axis, right? Okay, so let's draw it here. This is line number 1. This is our line number 1, L1. And it says x should be larger than or equal to, so the corresponding region is to the right of L1, right? Next, boundary line is y equals 0. Y equals 0 is just the x-axis. Okay, the x-axis here. And the inequality states that y should be larger than or equal to 0. This corresponds to the region up the line. Right? Okay, this is the second region. And next, we have a line that crosses 2 points, 0, 8, and 4, 0. 0, 8, let's suppose this is 8. And 4, 0. 4, 0 is about here. Third line crosses these 2 points here. This is our third line. L3, right? And inequality states that y should be less than or equal to. Less than or equal to corresponds to a region below this line. Okay, number 4. A line that crosses 2 points, 0, 5. 0, 5 is spelled here. And 10, 0. 10, 0 here. Okay, so this is our fourth line. L4. And inequality states that y should be less than or equal to, which corresponds to a region under this line, right? Okay, so now can you see what is the bounded region or unbounded region, if possible? Okay, the region is here. First of all, it should be to the right of the blue line here, right? And second, it should be up to the red line here. And it should be under the pink line and also under the green line here. Okay, so this is all corresponding area, which is a bounded region. It has 4 edges and 4 vertices, right? Okay, and according to this theory, we have learned we only need to check the value of the target function x plus y at these different vertices, right? So let's call them P1. Use another color. How about, okay, purple. Let's call them P1, P2, P3, which is actually the original point, and P4. Okay, and then we need to find the coordinates of P1, P2, P3, P4 first. Let's start from P1. P1 is intersection between L4 and L3, right? So let's combine these two equations of L3 and L4, which is equivalent to, let's put the equations inside. L3 is y equals minus 2x plus 8, and L4 is y equals minus 1/2 of x plus 5. And then we need to solve this equation, right? Which is minus 2x plus 8 equals minus 1/2 of x plus 5, from which we can get 3/2x equals 3, which gives us x is actually 2, right? And if we put 2 back into the original, one of the original equations, we can get y is 4, right? So the coordinate of P1 is 2, 4. Okay, and let's check P2 then. P2 is actually the x-intercept of L3, right? Which is 4, 0. So this is easy. We can just directly write its coordinates here. So how about P3? P3 is just the origin point, which has the coordinates 0, 0, right? And next, P4. P4 is here, which is the y-intercept of the L4, which is 0, 5. Okay, so now we have all the coordinates required to calculate the target function. Then we can draw a table to compare the different values of the target function at different vertices. So the first column usually to be different vertices. And second column is a target function, x plus y, right? First vertex is P1, coordinates 2, 4. Second, P2, 4, 0. Third, 0, 0. Fourth, 0, 5, right? And at each of these vertex, the target function is, okay, let's start from P1. Target function is 6. P2, target function is 4. P3, target function is 0 plus 0 is 0. And P4, target function is 5, right? Then you can see that at point P1, target function has a maximum value, right? Now we can make the conclusion. When x is 2, y is 4, the maximum of x plus y is 6, right? Okay. Now please have a look at this. Do you have any questions? No questions? Okay, let's move to the next one. All right, question 4. Find the maximum possible value for x plus y given that 3x plus 2y is less than or equal to 7 and 2x plus 4y is less than or equal to 8. Okay, there is a hint saying this is an optimization problem in an unbounded region. Okay, in an unbounded region, you need to analyze if the maximum or minimum exist or not, right? So let's have a look how we can do this. Let's start from the two constraints here. Okay, let's label them as 1 and 2. So first constraint is equivalent to 2y less than or equal to minus 3x plus 7, right? Which is equivalent to y is smaller than or equal to minus 3 over 2x plus 7 over 2, right? And corresponding line L1 is y equals minus 3 over 2x plus 7 over 2. And in order to draw this line on the 2D Cartesian plane, you usually will use its x and y intercepts, right? So x is, when x is 0, we solve y is 7 over 2. And when y is 0, we know that x is 7 over 3, right? Okay, number 2 is equivalent to 4y less than or equal to minus 2x plus 8, which is equivalent to y less than or equal to minus 1 over 2x plus 2, right? And corresponding boundary line L2 is y equals minus 1/2 of x plus 2, right? Okay, again, find its x and y intercepts. When x is 0, y is 2. And when y is 0, x is 4, right? Okay, so let's draw these two lines on the 2D Cartesian plane first. Okay, let's start from the first line. First line passes 2 points. 1 point is 0, 2 over 7. Okay, suppose 0, 2 over 7. Sorry, 7 over 2 is here. Next point is 7 over 3. So 7 over 3 is approximately 2.3, right? Well, let's suppose it's here. And our first line should look like this. This is our L1. And according to the inequality, y should be less than or equal to, right? Less than or equal to means the region should be under this line, right? Okay, second line. Let's use another color. Passing 2 points, 0, 2. So suppose 0, 2 is here. And 4, 0. 4, 0, let's suppose it's here. 4 must be greater than 7 over 3, right? Remember, you need to ensure the relative positions of each element is correct. Okay, so this is our line number 2, L2. And inequality states that y should be less than or equal to. This corresponds to a region that is below this line, right? Anything else? No, these are the only constraints we have. So what is the corresponding region? The region is just below the blue line and the green line. So the region should look like this, right? First of all, below the green line and all the way down here, and then below the blue line here. This is our region, right? We need to consider the optimization problem in this region. Note that this is unbounded region. So do we have a maximum or minimum? We need to analyze. Our target function is x plus y, right? X plus y. So because we have an unbounded region here, we can't just analyze the values of the target function at different vertices because we have infinite number of vertices because this is an unbounded region, right? So let's use another method. Let the target function x plus y equals m. And our target is to maximize value of m, right? So how do we do this? We convert it equivalently to an equation of line like this. This is equivalent to y equals minus x plus m, right? So m is just the y-intercept of this line, right? So the problem is that while keeping this line crossing this region, to what extent can the m be in order to maximize it? An intuitive thought would be, so note that this line has a slope of -1, right? So intuitively, this line should look like this, right? So can you see where should this line be in order to maximize the y-intercept m? At the first glance, it should be here, right? That means as long as this line passes through this vertex here, the y-intercept here is the maximum is maximized. Otherwise, if this line moves a little bit further up, this line cannot cross the region here, right? Understand? But in order to check that, we need to check the slope of this line first. For example, if this line has a slope like this, which is equivalent to the blue line, the answer should be different, right? The answer could be different, I mean. Or if this line has a slope like this, which is steeper than the blue line, in order to get a maximized y-intercept, it seems that in this case, the line should cross this point, right? So first of all, we need to check, we need to compare the slopes of these three lines. Okay, let's say slope of, let's call this line 3. Slope of L3 is -1, right? And next, we need to check the slope of line 1, which is the blue line. which is minus 3/2, right? And we also need to check the slope of L3, which is a green line. Green line has a slope of minus 1/2. So note that minus 1/2 is the largest value of the straight, right? And minus 3/2 is the smallest. And minus 1 is right in the middle of minus 3/2 and minus 1/2. This means the pink line should look like this. So if the pink line crosses point here, it should be looking like this, right? Because slope of the pink line is smaller than the green line and larger than the blue line. This means the pink line must be in the middle of the blue line and green line, right? Because the M is undetermined, so the pink line should be a family of lines that has different y-intercept, right? Now, can you tell me where should this pink line be in order to maximize its y-intercept, and as well as crossing the shaded region? You see that? Of course, this line should be here, right? Because if not be here, for example, if you move this line a little bit further up, this line cannot cross the bounded region, right? And if you move this line a little bit further down, this line crosses region, but the y-intercept is not maximized, right? Do you understand? Both of you, can you follow me? How about, okay, so let's make a note here. The line L3 should be here to max M, right? Okay, so that means this line should cross the point here, right? And we need to find the coordinates of this point. The point, let's call this P1. P1 is an intersection of L2 and L1, right? So it's an intersection of L1 and L2. So let's combine these two equations to find the coordinates P1. Okay, L1 is y equals minus 3/2x plus 7/2. And line 2 is y equals 1/2 of x plus 2. And we need to solve this equation, right? So x is 1/2. No, not 1/2, sorry. X is 3/2, and y is 5/4, right? Okay, so the intersection P1 is 3/2 and 5/4. Okay, so that means line 3 passes through P1, right? So line 3 passes P1. This means we can insert the coordinates of P1 into line 3, line L3. So 5/4 equals minus 3/2 plus m. And then we can solve for m, right? M is just 11/4, and this is the maximum value of m, right? Okay, so the conclusion is when m is 3/2, y is 5/4, maximum of x plus y is 11/4, right? Okay, please have a look at this. Any questions? No? Okay. Let's look at the next question. All right, next question. An airline offers coach and first class tickets. So there are two types of tickets, right? For the airline to be profitable, it must sell a minimum of 25 first class tickets and a minimum of 40 coach tickets. The company makes a profit of $2 to $5 for each coach ticket and $200 for each first class ticket. At most, the plane has a capacity of 150 travelers. How many of each ticket should be sold in order to maximize profits? Okay, so this is a typical application problem. We want to maximize the profits given a series of constraints, right? So in order to model it mathematically, first let's use some letters to denote the necessary variables, right? Okay, so basically we want to sell some of the coach tickets and some of the first class tickets. So we can use a letter X to denote the number of coach tickets sold. And use the letter Y to denote the number of first class tickets that should be sold. Right? And our target is to maximize the profit, right? What is a profit? So for each coach ticket, we make $2 to $5. We have X coach tickets. So from the coach tickets, we can make a profit of this number. And for the first class tickets, each ticket we can make a 200 profit, right? We have Y tickets. So profit from the first class ticket is 200 Y. So basically, we want to maximize the total profit here, right? This is our target. So our resource is limited. We cannot just sell unlimited tickets, right? What are constraints? So first of all, it states that we need to sell a minimum of 25 first-class tickets. So this means Y should be larger than or equal to 25, right? Next, a minimum of 40 coach tickets. This means X should be at least 40. And the total seats we sold is 150, right? So that means the number of coach tickets plus the number of first class tickets should be less than or equal to the total capacity of the plane, which is 150, right? So these are the constraints. And note that because X denotes the number of coach tickets and Y also denotes the number of first class tickets, both of X and Y should be integers, right? X, Y are integers. Okay, these are the constraints. Okay, so let's start from the constraints to see how we can maximize our target function. Okay, from constraint number 1, we can get a boundary line, it's called L1, which is Y equals 25, right? And from constraint number 2, the boundary line L2 is X equals 40, right? And constraint number 3 is actually equivalent to Y less than or equal to minus X plus 150. And the corresponding line L3 is Y equals minus X plus 150, right? So when X is 0, Y is 150. And when Y is 0, X is 150. Okay, so now let's draw all the constraints on the 2D Cartesian plane. Okay, first of all, first constraint is Y equals 25. This should be a horizontal line that is parallel to the x-axis, right? So this is line 1. And this should be 25. And line 2 is a vertical line that is parallel to the y-axis, right? This is line 2. Here is 40. Okay, line 3. Passing through 2 points. 0, 150 and 150, right? Okay, so this is a line L3. It is very easy to determine the relative positions of these 3 lines, right? Because 150 is larger than 25, and 150 here is larger than 50. So the red line must be like this. So this is a line 3. So can you see what is the shaded area? What is the constrained area? It should be here, right? Because according to all the inequalities, first, Y should be above L1. Above L1. And to the right of L2. And here it says y should be less than or equal to, which corresponds to the region under L3, right? So the shaded area here is all bounded area. We need to consider the value of the target function only in this area, right? So according to the theory, we need to check only the vertices, right? So let's call them A, B, and C. Okay, so next step, we need to find coordinates of A, B, and C respectively. Okay. Point A is an intersection between L2 and L3, which is x equals 40 and y equals minus x plus 150, right? And this gives us x equals 40 and y equals 110. So the coordinates of A is 40, 110, right? Okay, next, point B is intersection between L1 and L3, which is equivalent to y equals 25, y equals minus x plus 150, which gives us x equals 125 and y equals 25. So coordinates for B is 125, 25. All right, so coordinates for C is much easier, right? Because it's just the intersection between L1 and L2, which is 40, 25. Okay, so now we have coordinates for A, B, and C. In order to maximize the target function, we can use a table like this to check different values of the target function at vertices A, B, and C, right? Target function is 225x plus 200y. Remember that? So vertex A is 40, 110. Vertex B is 125, 25. And vertex C, 40, 25. Okay, so at vertex A, target function is 225 times 40 plus 200 times 110, which is 9,000 plus 22,000, which is 31,000. Okay, at vertex B, target function is 225 times 125 plus 200 times 25, which is 28125 plus 5,000, which is 33125. And at vertex C is 225 times 40 plus 200 times 25, which is 9,000 plus 5,000, which is 14,000, right? Okay, so now can you see which is largest? Of course, this is a maximum value, right? So the conclusion is when x is 125, y is 25, max of 225x plus 200y is 33125, right? Meaning when selling, what is your x? X is number of coach tickets, right? So that means when selling 1 to 5 coach tickets and 25 first class tickets, the profit, actually the total profit, right? Total profit is maximized to $33125, right? This is a whole process for this question. Okay, have a look at this. Do you have any questions? Okay, no questions. All right, let's see the last question. Health food business would like to create a blend of dried fruit in the form of a box of fruit bars. Decides to use dried apricots, which have 407 milligram of potassium per serving, and dried dates, which have 271 milligram of potassium per serving. The company can purchase its fruit in bulk for a reasonable price. Dried apricots cost $3.33 per serving, and dried dates cost $2 per serving. The company would like the box of bars to have at least the recommended daily potassium intake of about 4,700 milligrams, but would like to keep it under twice of the recommended daily intake. In order to minimize cost, how many servings of each dried fruit should go into the box of bars? All right, so this is another optimization problem, right? Because it says in order to minimize, it asks you to minimize cost given a series of constraints, right? So again, we use two letters to denote necessary variables. First one should be the number of servings of dried apricots, right? Second is the number of servings of the dried dates, right? We need to determine these two variables. So let X denote the number of servings of dried apricots, and let Y denote the number of servings of dried dates. Okay, so your target is to minimize cost. The cost comes from two sources, right? One is from the number of servings of dried apricots. So it says for apricots, the cost is 3.33 per serving. So that cost is 3.33x. This is the total cost from the dried apricots. And for the dried dates, the cost is 2 per serving. So when you have Y number of servings, the total number of cost from the dates is 2Y, right? We want to minimize the total cost, which is 3.33x plus 2Y. Given a series of constraints. So first, let's read the sentence. First constraint is the total number of potassium should be at least 4,700, right? So 407x. Why 407x? Because it says the dried apricots has 407 milligram of potassium per serving, right? So when you have X servings, the total milligram of potassium from the apricots should be 407x, right? And similarly, for the dates, the number should be 271y, right? Because here it says 271 milligram of potassium per serving for the dates. Okay, so the total number of this is greater than or less than, greater than or equal to 4700, right? This is the first constraint. Another constraint is keep it under twice the recommended daily intake. So second constraint is this number here must also be less than or equal to twice of the recommended value, which is 4700, right? Understand? And because X and Y denote the number of servings, so this means both of them should be positive, right? Positive or zero. So these are all the constraints. Okay, again, let's start from the constraint to see if we have a boundary region or not. So let's label them with 1, 2, 3, 4. Start from the first constraint, which is equivalent to 271y greater than or equal to minus 407x plus 4700, which is further equivalent to y is greater than or equal to minus 407 over 271x plus 4700 over 271, right? And of course, the corresponding line let's call it L1 is y equals minus 407 over 271x plus 4700 over 271, right? And next, let's determine the x and y intercept. When x is 0, y is 4700 over 271. And when y is 0, x equals 4700 over 407, right? This is the first line. Okay, second constraint is equivalent to 271y larger than or equal to or less than minus 407x plus 9400, which is equivalent to y less than or equal to minus 407 over 271x plus 9400 over 271, right? So the corresponding line L2 is y equals minus 407 over 271x plus 9400 over 271, right? So when x is 0, y is 9400 over 271. And when y is 0, x equals 9400 over 407, right? Okay, so first two constraints have been taken care of. Third constraint, this is simple. This means line 3 is x being 0, right? Because it says x is larger than 0. Okay, false line is y equals 0, right? Okay, so now we can draw the 2D, draw all the lines onto the 2D Cartesian plane. Okay, y-axis and x-axis. So first line passing through 2 points. First, 0, 4700 over 271. Suppose it's here. I suppose this value is here. And x-intercept is here. All right, so this is our first line. L1. And inequality states that y should be larger than or equal to, right? Larger than or equal to means the corresponding region is above this line. Okay. And second line, passing through 2 points. One of the point is 9400 over 271, which is larger than 4700 over 271, right? And the x-intercept is 9400 over 401, right? Actually, the y-intercept is twice of the y-intercept of L1, and x-intercept is twice of the x-intercept of L1, right? If you notice that. So these two lines are actually parallel to each other, right? Okay. Again, my drawing is not necessarily to scale. So as long as you ensure each element is in its right position, you'll be fine, okay? This is L2. And inequality states that y should be less than or equal to means the corresponding region is under this line, right? Okay. So anything else? Anything else? Yes, we have line 3. Line 3 is x being 0. X being 0 is a vertical line like this, right? It look like a vertical line here. And constraint 3 says x should be larger than or equal to. That corresponds to the region to the right of this line. The line 4 is a horizontal line, y being 0. And constraint states that y should be above this line. Okay, so now can you see what is the bounded region? We can draw from here, right? Bounded region should be to the right of the red line and under the blue line, under the green line here, and above the pink line here, and above the blue line here. So this is our bounded region. Okay. And we need to consider different values of the target function here in the bounded region. So first of all, we need to decide what are the coordinates of the vertexes of the bounded region. Let's call them point A, point B, point C, and point D. Okay. Okay, so how can you decide the coordinates of these vertices? Actually, these are pretty simple, right? They are either the x-intercept or the y-intercept. So, A is a y-intercept of line L2, right? So the coordinates of A is 0, 9, 4, 0, 0 over 2, 7, 1, right? How about point B? Point B is the x-intercept of L2, which is 9, 4, 0, 0 over 4, 0, 1, 0. Okay, how about C? C is x-intercept of L1, which is 4, 7, 0, 0 over 4, 0, 1, 0. And point D. Point D is y-intercept of L1, which is 0, 4, 7, 0, 0 over 2, 7, 1, right? Okay, so now we have all the coordinates of the 4 vertices. Now we need to check the different values of the target function at these vertices. Again, we can use a table to illustrate this. A 0, 9, 4, 0, 0 over 2, 7, 1. B 9, 4, 0, 0 over 4, 0, 1. C 4700 over 4, 0, 1. And D 0, 4700 over 2, 7, 1, right? Target function is 3.33 dx plus 2y. So at point A, this value is 0 plus 2 times 9400 over 271, which is approximately the 69.3. At point B is 3.33 times 9400 over 401 plus 0, which is approximately 78.1. And at point C, value is 3.33 times 4700 over 407 plus 0, which is approximately 39.0. And at point D, this value is 0 plus 2 times 4700 over 271, which is approximately 34.7. And as you can see here, this number is a minimum number, right? And now we can make the conclusion. So when x is 0, y is 4700 over 271, which is approximately 17.3. Minimum of 3.33x plus 2y is 34.7, right? And back to the question. X is number servings of dried apricots. So that means was to $34.7. Right? Okay, so final conclusion is when number of servings of dried apricots is 0 and number of servings of dried dates is 17.3. The total cost is minimized to $34.7. Okay, please have a look at this. Do you have any questions? Okay, so